the world's first electronic computer.
In 1 second, the computer can perform more than 1 million arithmetical operations.
Advanced microprocessors like the 286 or the 386.
Potential Y2K computer crashes top the list.
And we are calling it iPhone.
It's part of a popular movement in the technology industry. It's called cloud computing.
And you'll see why 1984 won't be like 1984.
Hello, and welcome to Magnetic, the History of Computing. This is episode 12, Landing the Eagle. Last time, we talked about the huge strides NASA made to get a computer miniaturized and placed inside of the Gemini capsule. They also expanded their computing power to handle tracking and communicating with two spacecraft at the same time. In 1964, we see the merging of three of NASA's major networks into one called NASCOM. If you remember these from episode 10, the Manned Space Flight Network, MSFN, the Deep Space Network, DSN, and Satellite Tracking and Data Acquisition Network, or STADAN. Those three are now one big network called NASCOM, which I'm assuming is short for NASA Communications. Before I get too deep into this episode, I have to share something I found really interesting. I read a quote while researching this episode that shows the gravity of this mission. It is a quote from an article entitled, "Electronic Navigator Charts Man's Path to the Moon." Author A.L. Hopkins says, quote, "If the designers had known then, in 1961, what they learned later, or had a complete set of specifications even been available, they would probably have concluded that there was no solution for landing on the moon with the technology of the early 1960s. Basically put, this was impossible, but nobody would have known, and they did it anyway. That's admirable, and thinking about what was accomplished during this time tells me that sometimes you just have to go blindly for a dream when you have one. Now we are well into the Apollo design phase. Since Kennedy's assassination, America has taken a more serious look at the space race, and the government has doubled down their investments into spacecraft. The first contractor, MIT, has joined the design team with an open door, which kind of made others ask, where was the bid? See, the engineers at MIT came on board easily and without question, probably because their director, Charles Draper. He had invented and worked with a unique system that measured exactly what the pitch, roll, and yaw of a flying vehicle was at any time. As a quick aside, pitch is the aircraft nose pointing up and down, roll was it going side to side, and yaw was it spinning side to side, nose to tail. It required a lot of math. This inertial measurement device was used in the 1950s to send an airplane into autopilot for the first time. NASA liked it, but would need more if it were going to be used to fly to the moon. So Draper overlaid an old U.S. Navy tool called a sextant on top of this navigation device. Then he added a computer to handle the calculations. It's just a matter of fitting the large inertial measurement device, known as the gimbal, and a computer into the small phone booth-sized thing. So in comes a new small computing module called the navigation computer. It, along with a couple of other modules that were developed, came to be known as the fourth crew member on Apollo. It was important to try to squeeze this computer and other modules into this small capsule. See, astronauts had to make quick decisions during each mission, and given the distance from Earth, they would have to wait 1 to 5 seconds for signals to get to or come from mission control via the RTCC. The entire system was impressive and actually provided timing for 20 onboard spacecraft systems. The Apollo computer relied on the new integrated circuit chips, or ICs, which we previously talked about. However, this was the first use of these instead of discrete components. Discrete components were soldered transistors on a printed circuit card, whereas the ICs were extremely compact and manufactured with very small transistors already on them. All of this stuff ran software, of course. Software for all of those 20 onboard systems that talk to each other, and the UNIVACs and IBMs on the ground. The job market for software writers or engineers was excellent at this time. The job title, software engineer, was a new thing at the time. They were looked upon like a mundane thing from the general public, but in the end emerged as the most important part of the NASA program. Life was tough for these software engineers. The process they went through was arduous, but it was the only way to do it at the time. Software programs were written by hand and then written onto punch cards. The output was online printer paper, which was used to review the code. Once that looked good, the program was written to tape. In order to get the program loaded into the capsule memory, it was written to core rope memory. Core rope memory, also known as fixed memory, was developed by hand by mostly women by means of sewing wires onto rings on a certain position, which took months. In terms of binary code ones and zeros, a 1 ring goes through the core and a 0 ring goes around the core. It all had to be correct, and once it was made, it could not be changed. To be a software engineer in MIT for NASA, you had to learn the language of the program. The language was a form of assembly called AGC, which stood for Avionics Guidance Computer. The code took a long time for MIT engineers to write, but they had to do it fast because the clock to the end of the decade was ticking. Of course, anytime you rush something, you can't expect it to be great. So the initial drafts were pretty poor in quality and therefore took even longer to validate the code. It was getting so bad that the software ended up causing delays to the entire program. The software itself was under scrutiny because of its size, too, most of the time being too large to even run on the rope memory. One program exceeded the memory by almost 12,000 words, or 75 kilobytes. If you can imagine, you're counting words and characters like this in the code you're writing because you barely have any room in the memory. And then when you're done, you're told that the code exceeds memory space by 11,800 words. NASA realized that there were excessive problems with the code, so they hired a man named Howard Tindall back in Gemini to be the watchdog for MIT's software. He was shocked at what was happening with the software engineers and their output. He would be so upset at what he saw that he would write what became known by others as Tindallgrams, which were blunt memos regarding software development for Apollo. I'm assuming that if your name made it onto one of these Tindallgrams, you were probably having a bad day. In one Tindallgram, he wrote that the software itself would end up pacing the whole mission. Not astronaut training, not construction of the lunar module or command module, but the software. So, to fix this issue, MIT went into emergency mode and reacted in the worst way. They threw more programmers into the office. Basically, MIT was throwing more of this rushed programming done by people who, like all of the NASA staff, didn't get enough sleep. NASA reacted by having MIT work with their competitor, IBM, on the implementation of software checking during development. It basically means that they were required to check if the software functions to make sure they work before moving on. Seemed like a good idea. However, testing the software that MIT was coding was expensive too. When they wanted to test, they'd run a simulation and make sure the software was doing what it was supposed to. So to do that, they bought a couple of new computers, like two of the 360-75 models from IBM, and also the new and quite nifty Honeywell Model 800 and two of the Honeywell 1800s. The final process of this whole software engineering bit was to take these big, beautiful mainframes and load the program onto them through their handy-dandy punch cards and magnetic tape. Then they ran them at a peak 4,500 CPU hours a month. MIT ran between 50 and 100 test runs of 2,000 words at a time to fully debug the software. By the time they were ready to deliver the final flight program, they had to run it between 1,000 and 1,200 times. It was a quite lengthy and time-consuming process. Time and money. Just testing this stuff was 60% of the budget, and that was for those Honeywell mainframes, some test operators, and someone to develop the software to simulate the whole thing. For all the software development and testing, all the drama in the new hires, the stress that everyone was feeling, here's what ended up happening in 1967 when it was all being put together. It was getting close to go time and the Apollo flight software had finally been delivered. Integration testing was going and Mr. Tindall was not happy. There were software bugs in every module, though the individual modules had been tested and were bug-free on their own merit. The modules just didn't integrate with each other well. So debugging on an integration level began, and delays were on the forefront. No changes to the software were allowed, which meant that if any of the crew requested a new or modified feature, it was denied because it would have caused even more delays. Remember, the code was sitting on a bunch of wires and rings installed in the capsule, so changing that would have been impossible. Future programs being developed for other Apollo flights had to be set aside because MIT was still running debugging for the first program on those big Honeywell mainframes, and they only had 2, so there was no room for others. Needless to say, the quality of the software was substandard, but it was at a point that if there was a bug, the crew would be able to work around it. For example, the Apollo 1 crew on January 23, 1967, was running a simulation, and the computer's calculations were off by as much as 138 seconds. The rope memory was installed, so there was no fixing it. The only thing they could do is receive calculations from RTCC and manually key them into the computer. It was manual synchronization of the clocks. Sadly, just 4 days after that simulation, the first Apollo mission resulted in tragedy. The crew, consisting of Mercury astronaut Gus Grissom, the first man to walk in space, Ed White, and rookie Roger Chaffee, was consumed by a flash fire by faulty wiring, which was another quality issue. This tragedy caused the delay that was needed because it forced everyone to take a good hard look at the quality of things they were creating. Quality became the focus for the rest of the program. The Apollo program produced amazing results and achieved sending men to the moon, 16 of them actually, who came back to celebrate with the rest of the U.S. to tell their story. Very few problems with software and hardware were encountered after the tragedy of 1967, except for those 1201 and 1202 alarms Neil Armstrong and Buzz Aldrin encountered when trying to land on the moon for the first time. But that was the computer working the way it should. It had too many programs to run because Buzz had turned on the return radar too early, so it dropped low-priority programs. It didn't crash, though. Sometimes it had to be rebooted, like in Apollo 12 when the capsule shut down in the middle of liftoff, but that's because it was struck by lightning on the way up. One last time it was looked at was during Apollo 13 when all the instruments started going crazy, but that was because of a burst oxygen tank. Actually, Apollo 13 is incredible to listen to as a person who fixes things for a living. Hearing them work through that mission is incredible. So as we wrap up Season 1, we've taken the development of computing through thousands of years and we've arrived at a place where we got it right. In the next season, we're going to miniaturize these computers. We're going to put them into small boxes that fit on your desk and even smaller boxes the size of a notepad. Thanks for listening to this season. It's been a true honor. We'll be offline until September to do more research and development on Season 2, and you're gonna love what's coming up. Thanks for tuning in. We'll catch you on the next leg of the journey.